Right. So from everything we've been doing applied electricity so far, we've been using this as our basis. V is equal to IR, where this is the Ohm's law, right? And then what we've been doing so far is mostly about direct current, right? Which we, if you've heard, you see DC, 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 right? But this time around, we talk about AC, and then we'll be looking at it, some few terminologies and some understanding. Okay. So what we know about DC so far is, let's say, let's go back here, right? And we said few things about this, that mostly this is based on a device being used, and right, we have a voltage generator, right? And then we have a current generator as well, right? So most of the times, so here what we are doing is that we're talking about this V and then the I here, right? Okay. So AC and DC. What happens is that when we say DC, what it means is that the voltage and the current from the generators, right? They don't change with time. So you see, when you see this particular graph here, right, we have time, right, and then these are the quantities, whether it's voltage or current, right? And then if it starts from, let's say the time is five, let's say 2 seconds, right, 4, 6, at any time or at any point in time, if you check the voltage, right, if you check the voltage and the current, it will be the same. So that's what we mean by direct current. Okay, but then here's what we have. But then what comes next is the alternating current. What we see about this is that the same graph, right? So we have time here. We are checking the voltage and current as a function of time, right? Time, right? So then the voltage, the purple line, right? The current, yellow line, right? Then again, this is just 300, so that's why they are a bit apart. Appropriately, they should be together on the same line. But then there's also another case where they are not so in line. Talk about that later. So the AC says that for the current or the voltage from the generators at any point in time is different, right? So let's see if we have about, let's see, 2 here, 4 here, and about 6 here, right? We could have about 8 here, we have about 10 here, and we have about 12 here, right? So let's see, 1, 2, 3, 1, 2, 3. Okay, yeah, you could have about 12 here, right? Right. So at every point in time, when you try to trace back down, so let's say at about, let's say seconds, right? So about 2 seconds, if you check different voltage. About 4, when you check different. 6, the same throughout, right? So that's what we're seeing. And then most of them follow a particular pattern, right? So you can see that for commercial voltage, what they call voltage sources or current sources, they follow a particular pattern. Just to make sure that it's stable enough and less distraction. We could predict what's happening. So that's it for AC, right? So voltage, current. But then it's not always that the behavior of the curve will be in this way. It could be something of like this. It could be like this. It goes on. So it starts at a particular voltage or current, right? It goes for a particular time and then it comes down, right? And it goes negative or something, right? It holds, right, for a particular time, goes up. So the curves could be different, or it could even be a combination of some other ones. So this one like this, it goes like this, kind of like sinusoidal, it goes triangular, right? And then repeats itself again, right? So yeah, so that's also another thing. And as we look at this, let's look at some few terms. So when you look at this one, for instance, when you look at this, just by the way, this looks like some kind of sinusoidal curve, right? So if you plot a sine wave, you get something like this. Okay. So when you look at this one, for instance, you see that it starts at a particular place, right? It starts somewhere, let's say from the origin of the graph, 0, right? It moves, it gets to a particular highest point, a peak, right? A peak, and it drops back here. And now it goes to the other side, sort of like negative, right? It goes, comes here, negative peak, and then it goes up, right? So the point where it's maximum, right? So you could have about something like, let's see. So this point here could be V max, or you just write it M, or I max, IM, right? So this is what we call maximum, or at times you say peak current, right? Peak voltage. Yeah. Peak current, peak voltage. That's what I see. And then another thing too is that when you look at, so let's use this particular third example. When you look at this particular one, you see that it follows a pattern, right? So let's see. And then the pattern sort of repeats itself, right? So let's see. So we look at this one, for instance, it gets some kind of semicircle. So let's say a sine wave or something, right? and then gets a right angle triangle, right? And it ends, right? And then it continues again, but the same shape, right? From here, here, and here. So you could see clearly that this is what we call a cycle for this particular sinusoidal and current, sinusoidal voltage or current. It has a particular shape. So this one here, when it goes one of this is what we call a cycle, right? So cycle. So this is basically one cycle, right? And the time it takes, so you see we are doing everything against time, and the time it takes for it to be able to complete just one cycle is what we call a period, right? Period, which is t, right? And then we have another quantity that help us to describe these AC currents or voltages, right? Which we say is we call frequency, right? And then the frequency is sort of related to the period. So we just say the inverse, let's see, the reciprocal rather. So we say is the reciprocal of the time, right? So this or the period, right? So yeah, this is the basic understanding. Okay, so V is equal to IL, but then this one is based on the device, but the V and then I are the sources, right? They are the sources. They could be from the generators, so voltage generators, current generators, and then they change with time. DC or direct current, constant with time, right? Doesn't change, remains the same throughout. But AC moves, change with time, right? It could be of this way, of this waveform. This, so when we draw a graph like this of the voltage or current against time, that's what we see is a waveform, right? So it could be something like this, or we say sinusoidal. It could be something like this, which looks like a rectangle or something, and this looks like a combo. It could even be just triangles, right? You could have something like this. There's the time. You could have something just like this, right? Or it could be any way, right? Could be any way. Could be any way at all. Okay, but then let's see. What happens is that whenever we are using any of these, each and every one of them, whether AC or DC, they have their own advantages, right? But then there are some things that they have with this when we are doing this discussion. They are very important. So let's say you have let's see, a circuit, right? Let's say there's a voltage source, right? Let's say this is your resistor, right? Let's say a resistor. Resistor. Okay. Right? If you pass AC current through it, there will be a particular response that you get, right? If you pass DC through it, there will be a particular response that you get. Okay. So DC, AC. Now we know what these terms mean, right? So if you pass any of this through it, there's a particular way or response that or feedback you get from the circuit, right? So what it says is that if you have a particular AC current, right, and then you find something we call average of it, right? So you find the average. You find a way to find the average of the AC, right? This will give you what we call the, so let's say average of the AC, right? You can find the average of the AC and to give you a DC, right? Equivalent. But then for this particular one, the average won't give you the same effect. So let's say you have an AC voltage or current generator or source, right? If you find the average and it gives you a DC, when you apply this AC to the circuit here, right? When you apply the average of the AC, which is the DC that you found, to the circuit here, the response you get won't be the same, right? So basically, this is what we call the average here. The average of the AC, right? The average value for the AC can give you a DC. But then again, we have another one which is much more effective, right? So the term for that one, so let's just number it. So the term for that one is what we see effective value. So this is what we see average value. Let me write it here. Okay. Okay. This average value. Okay. Average value, right? And we have effective value. Okay. Of DC. Or AC rather. Of AC. That also can give you a DC value, right? but there's a difference. So the average value, you find it, you can find the average value of the AC gives you a DC. But then if you pass the original AC through the circuit and you pass the average value you found through the circuit, you won't get the same response. There will be a differences in the response you get from the circuit, right? But then the effective value, what it says is that the effective value, or at times we have what we say RMS, right? The RMS basically means root mean square value. Right? What the RMS says is that if you have an AC quantity, right? If you have an AC quantity, right, and you are able to find the effective value of it or the RMS value of that AC quantity and get a DC, this will happen. If you have that particular, let's say in this particular circuit here, the voltage source here, and just by the way, there's a way to represent the AC and then DC voltage sources. A bit different, but yeah, they are similar. So let's see. I'm just going to write that and continue what we are discussing. So let's say we have a voltage, right? So let's use a voltage. Okay. This. So most of the times you see some kind of just curve in it, right? And we just see this. Say there's a current voltage rather. So we just try this. I think you just see this one in it. So what the difference between the, so we've talked about the average value of the AC. Now we're talking about the effective value of the RMS or the root mean square value of the AC. And we said both of these give us a DC value, right? And then we said the DC, if you have you take the average of the AC and you find the DC, when you apply the original AC to it and you apply the average, which is the DC you find to it, the response will be the same, right? Now the effective value, so now we are done with this. Right? The effective value of the AC or the root mean square value of the AC, which also gives us DC. What this says is that if you have the original AC, right, and you pass it through a resistor, right, so you pass it through the same resistor. So these are the key terms: same resistor, right? Same resistor, same time, or let's say period rather, right? So you apply an AC, right, through a particular resistor, the same resistor for the same time period. If you, after you found the, what's the name, the effective value of the RMS value of that same AC voltage or current, and that DC that you found, you pass it, or the root mean square value or the effective value, you pass it through this same resistor, the resistor will produce the same amount of heat, right? So you see clearly that the average value doesn't give you the same kind of feedback, right? But then the RMS value or the effective value, the same, they are the same thing. Effective value, RMS value, root mean square value will give you the same response from the circuit. So that's what we're saying. And then, so this is the basic understanding. But when it comes to the equations, right, that help us to actually be able to describe these things. Okay,